Hi, it's me again, AJ, and today I am making a video tutorial about highest order ordinary differential equation. So, let's start. So, I have two problems here about higher order ODE. For number 1, we are asked to find a complete solution of the equation quantity d minus 1 raised to the power of 3 times y equals 2 times e to the x over x squared. And for our number 2, we are also asked to find the solution of the equation y triple prime minus 2y double prime plus 10y prime equals 3x times e to the x, which will satisfy the given conditions of y equals to negative 1/3, y prime equals to 0, y double prime equals to 1/3 when our x is 0. So let's solve for number 1. Problem number 1. In this problem, we're asked to find its complete solution. And as you can see, the given is a non-homogeneous type of equation. Why non-homogeneous type? Because our g of x has a value which is equals to 2 times e to the x over x squared. In higher order ODE, we have two types of equation. First is the non-homogeneous type, and second is the homogeneous type. When we say homogeneous type, our g of x has a value of 0 or equal to 0. And when we say non-homogeneous type, our g of x has a value. So in here, in our given equation, this is a non-homogeneous type because we have a value of g of x. So note that also that in calculus, differentiation is often denoted by the capital letter D, that is dy over dx equals to d sub y equals to y prime. The symbol D is called a differential operator because it transforms a differential function into another function. So in here, we need to transform D into y prime for us to solve it easily. So now, in equation 2, we are done in transforming it. So let's proceed to the next step. So in order to solve the complete solution, we need to find its complementary function, which is denoted by yc, and particular solution, which is also denoted by y sub p. So the complete solution of the non-homogeneous equation is y equals to y sub c plus y sub p. So to solve for our complementary function, we must first be able to solve the associated homogeneous equation, which is just setting the equation equal to 0. When we say associated homogeneous equation, it is just a relative to our homogeneous equation. So in here, we just need to equate it to 0, or making our g of x equal to 0 for us to solve a non-homogeneous equation. Remember that if you have a non-homogeneous equation, you need to transform it into a homogeneous equation before solving, because you can solve it easily without transforming it into a homogeneous equation. So now, for the next step is, this time, your equation becomes a homogeneous linear equation with constant coefficient. To solve this, we get the auxiliary equation, the roots, and the corresponding general solution. So as we factor it out, we found out that our m sub 1 equals to m sub 2 is equals to m sub 3 is equal to 1. So equation 4 and 5 shows the factorization part. So in equation number 5, we see that this the value of m's are equal or is equal to 1, so which falls to case 2, which is repeated real roots. And just by substituting the values of m's to the general solution, which is y equals to c sub 1 times e raised to the power of mx plus c sub 2 times x times e to the mx plus c sub 3 times x squared times e to the mx. So by substitution, we can get our complementary function, which is our equation number 6. So for the first part, this is our final answer for complementary function. Now we are done with complementary functions. Let's go on to the next step, which is finding for the particular solution. So next. So to solve for yp, we use Wronskian equation. Since the method of undetermined coefficients by superposition approach is not applicable to the equations of form number 1, which is our equation, because our g of x has a value of 1 over x squared, which is not or which cannot be solved using undetermined coefficients, because undetermined coefficients has its own limitations. So these are the following values of g of x which cannot be solved using undetermined coefficient. So if your g of x is equals to ln x, or 1 over x, or tan x, or sine inverse x, well, you cannot use the method of undetermined coefficients. So don't worry if you cannot use it, because we have another equation to help us to solve the problem. So in here we will use the method of variation of parameters, and this method uses Wronskian equation, which will help us to solve the problem. So from our equation 6, we get the value of y sub 1, y sub 2, and y sub 3. These values of y will be used in finding the determinants of our Wronskian equation. So let's go now. So don't mind this part because we're not reaching here yet. So let's first go to the Wronskian equation. So in here, I find first the differentiation, the y prime and the y double prime of each y values, because we will use them in finding the determinants of our Wronskian equations. So as you can see in this part, you see the formula of Wronskian equation, and in here I also summarizes the process. So all you have to do is to substitute the values which correspond to the values over here. So there's also another method of solving Wronskian. You can use the rule of Sarus, which is just multiplying the diagonal lines over here and subtracting it from the other side. Just go over the internet and you can already see it. So by substitution rather, we get the determinants of our Wronskian equations. So namely, w is equals to 4x squared e 3 to the x, and y sub 1 equals to the quantity of minus 2x minus 3 times 2e to the 3x, and our y sub 2, w sub 2 rather, equals to minus 4e raised to the 3x over x, and our y sub 3, I mean w sub 3 is equal to 4e 3 to the x over x plus 2 times e 3 to the x over x squared. So now we already have the values or the determinants of our Wronskian, and in this part we are going to use them in solving for our particular solution. So let's go back. So through using the determinants of Wronskian equations, we obtain the values of the u sub